So the AI boom is here, and it is changing everything. But what's the hidden environmental price tag? Today, we're going to build a formula to actually figure that out, breaking down one of the biggest and, let's be honest, often invisible costs of our new digital world. Okay, let's just dive right in with a number that really sets the stage: 1,050 terawatt hours. That's the International Energy Agency's high-end projection for what data centers worldwide could be gobbling up every single year by 2026. It's a truly massive figure, but, what does it actually mean? Well, to wrap our heads around that, get this. That much electricity is about what the entire country of Japan consumes in a year. We are talking about a nation-state level of power demand just to run data centers. It's kind of mind-boggling. But here's the thing. A huge energy bill isn't the whole story. Not even close. Just knowing the total power doesn't actually tell us the real environmental impact. The real question we have to ask is, where do the emissions actually come from? Because it's a lot more complex than just one big number. So let's build our formula together and get to the bottom of this. We'll start with AI's accelerating footprint, then we'll break down our three-part formula for carbon: the raw electricity bill, the grid's carbon, and what I like to call the hardware's ghost. Then we'll layer on the compounding water cost before we try to balance that final equation. All right, first up, AI's accelerating footprint. Before we can even start calculating, we have to grasp the sheer speed and scale of this new demand. We are not talking about slow and steady growth here. This is a full-on boom. Okay, so let's get into the first real variable in our equation, the electricity bill. This is where we just try to quantify the raw power that all these AI workloads are actually consuming. And this chart just illustrates that explosion perfectly. Back in 2022, global data centers used around 415 terawatt hours. But look at these projections. Some of the high-growth scenarios are suggesting that AI demand by itself could hit 1,000 terawatt hours by 2030. That's a potential jump of 160% in just a handful of years. Now, here's something that might surprise you. You might think training these giant AI models is the biggest power hog, right? And yeah, it's super intensive. But the real long-term energy driver is something called inference. That's just the continuous daily use by you, me, billions of people, asking questions, generating images, and using all these AI tools. That's what really scales up. All right, on to the second part of our formula. And this one is absolutely critical: the grid's carbon. The main takeaway here: not all kilowatts are created equal, not by a long shot. To really get this, we need to understand a core concept: carbon intensity. It's basically just a measure of how much carbon dioxide gets pumped out for every unit of electricity you use. Is your power coming from a coal plant or from a wind farm? That difference, it's everything, and it all depends on the local power grid. So this means the exact same AI task has a totally different carbon footprint, depending on where in the world it's processed. Running a huge workload in a region in the US, where the grid is still around 40% fossil-fueled, is going to generate way more emissions than running that exact same workload in a place like Sweden, which has a much cleaner, low-carbon grid. Location is everything. And this leads us to a really crucial problem: the capacity-timing mismatch. You see, even with these huge commitments to renewable energy, tech companies are building new data centers faster than new clean energy projects can actually be built and brought online. So you get this gap, and it forces these power-hungry facilities to just pull from the existing grid, which, you guessed it, often means burning more fossil fuels. Now for the third, and maybe the most invisible part of our emissions equation: what's called embodied carbon. I like to think of it as the hardware's ghost. It's the hidden environmental cost of just manufacturing all this physical stuff in the first place. Think about this. Before a single data center is ever switched on, a massive environmental debt has already been racked up. Making the specialized GPUs, the servers, the cooling systems, it's incredibly energy intensive. Those semiconductor fabrication plants, they can use millions of gallons of ultra-pure water every single day. All of this happens before a single query is ever run, and it's often completely left out of the total calculation. So we have our three-part carbon formula. But there's another really critical resource that we need to add to the equation, one that AI consumes in absolutely massive quantities: water. To make this real, check this out. An analysis from MIT suggests that asking a single complex question to a service like ChatGPT could use about 0.5 liter of water. That's basically a standard water bottle just for cooling the servers. Now imagine multiplying that by billions of queries every day. And when you scale that up, the number becomes truly staggering. By 2030, US data centers alone could be withdrawing up to 6.6 billion gallons of water every single day. That is a huge new strain on our water systems. And what's really critical is where a lot of these data center hubs are being built, in places already facing serious water stress. I mean, look at this table. Phoenix, Arizona is rated as extremely high for water stress. So this isn't just about using water. It's creating direct competition for a scarce resource with cities and farms in those regions. Okay, so let's put all the pieces of our formula together now. Let's see what the final balanced equation of AI's environmental cost really looks like, and maybe what the path forward is. What we really have here are three interconnected pressures, and they're all compounding each other. First, you've got that accelerating demand for electricity. Second, you have a growing withdrawal of water, often in places that can least afford it. And third, you have these grid capacity constraints that are holding back our ability to integrate clean energy fast enough to meet all that new demand. So what do we do? Well, a key takeaway from researchers is that we can't effectively manage what we aren't accurately measuring. They're calling for standardized, mandatory environmental disclosure from AI operators. Something kind of like the financial disclosures that companies already have to make. Without that kind of transparency, we're all pretty much just flying blind. And all of this leaves us with a final, really crucial question to think about. As this technology keeps growing, and it seems to be growing faster than our ability to even measure its full impact, what is the true cost of progress that we're actually willing to accept?